Good day, students. I hope I find you well. Welcome to yet another exciting edition of my chemistry lesson. Today I've just decided to focus on one of the interesting mechanisms that we find in organic chemistry. I'm going to focus on a class of organic compounds which is known as halogenoalkanes. If you still recall, in one of my videos I focused on free radical substitution, whereby we had alkanes undergoing free radical substitution, and then the alkane was changed to a halogenoalkane. So I thought I could link today's lesson to that previous lesson on on alkanes and free radical substitution. So if you look at the board here, I have a halogenoalkane. Now, simply put, what is a halogenoalkane? If you focus on the name, there is an alkane part, and then there is halogeno, meaning to say we have connected an atom of a group 7 element, which could be fluorine, it can be chlorine, it can be bromine, it can be iodine. So we have a halogen atom sitting on an alkane. So the complete name, it is called a halogenoalkane. Now, if you have an alkane molecule like ethane, it is non-polar. But the moment you introduce a halogen into the molecule, you also introduce polarity, okay? So we can actually say the electrons in this bond are not going to be shared equally, okay? There is a highly electronegative atom there. So this part, okay, will become negatively charged, okay? And that part becomes positively charged. So we have a carbocation ion there. And the moment you have a carbocation ion, it is susceptible to nucleophilic attack, okay? If you could still remember, compounds that we call nucleophiles, I'm just going to put examples of nucleophiles in this corner, okay? Nucleophiles can be classified into two parts. A nucleophile can be a negatively charged ion such as cyanide or the hydroxyl ion, okay? So they could be negatively charged ions. They are nucleophiles because they are going to attack the positive sender. They have great love for positive carbons. That's why they are called nucleophiles, okay? So there are two types. Either they can be charged, or you can have neutral molecules such as ammonia or H2O, okay? So two classes, neutral molecules or charged ions, okay? What makes these special is the fact that they possess non-bonding electrons, and as such, they could use the non-bonding electrons also to attack positively charged carbon senders or carbocation ions, okay? Right, so we just want to focus on the mechanisms of halogenoalkanes, and we are going to use nucleophiles, and we are going to carry out substitution. So the complete name of the mechanism is called nucleophilic substitution, okay? Simply because we are using nucleophiles and we are going to substitute. The mechanism is now called nucleophilic substitution, okay? So halogenoalkanes undergo nucleophilic substitution. We are going to substitute and we are going to be using nucleophiles, okay? So we call them the process nucleophilic substitution. Okay, now let's bring our nucleophile and let's trace what's going to happen, okay? So we want to, the nucleophile wants to reach the positively charged carbon atom there, the carbocation ion. The nucleophile cannot attack from here because it's negatively charged. So it will approach the carbon through this one, which we could call some form of backside attack, okay? So our nucleophile will attack from this angle, okay? So it will be my nucleophile here with its lone pairs, okay? And then it's going to attack the carbon, okay, from that side, okay? Please take note, in organic chemistry, movement of electrons, we use curly arrows, okay? And look at how the arrows are moving. They are moving in a systematic way. You have the hydroxyl attacking that way, and the electrons in this bond between the carbon and the chlorine, they're also shifting that way. So there's a systematic movement of electrons. Remember, for all mechanisms in organic chemistry, you should indicate movement of electrons using curly arrows, okay? So this process is simultaneous. We are forming a bond here, and that bond is breaking, okay? So the whole process is just one stage, okay? The whole process is just a one-stage reaction, okay? Because what's going to happen here is we're going to form a bond there and we're going to break that bond. So if you look at the reaction kinetics, for instance, the rate of this reaction is dependent on the concentration, okay, of your halogenoalkane and also on the concentration of your nucleophile, okay? So this reaction is a bimolecular, okay? Because it depends on the concentration of that hydroxyl and also the concentration of the halogenoalkane. It's a bimolecular mechanism, okay? Because it's a bimolecular mechanism, we can also use this word, okay? It's SN2, okay? Nucleophilic substitution depending on two molecules, and therefore we call it SN2, okay? It's a bimolecular mechanism, okay? The speed of this reaction will be affected by the concentration of the nucleophile and the concentration of the halogenoalkane. And in organic chemistry, we can say this one is a bimolecular mechanism. If you were to draw a reaction energy profile diagram for this reaction, okay, you could actually have it like this, okay, right? You have like that, and then your reactants, which are the halogenoalkane, and your products, which will be ethanol, okay, down here. And then you have your activation energy as usual, and then your intermediate, okay, will be up there. It's short-lived, okay? But we can actually complete what's going to happen after what I've shown there, okay? So I'm going to wrap this, okay? I'm going to wrap this so that you can see the product which is going to be formed, okay? Right, so after this process, okay, we are going to have, okay, our product in this way, okay? The halogenoalkane is now going to be changed to an alcohol, okay? So this one was chloroethane, okay? This, we call it chloroethane, but we now have ethanol, okay? So nucleophilic substitution of halogenoalkane using OH, hydroxyl nucleophile, will change the halogenoalkane to an alcohol. This is a one-stage reaction, okay, which depends on the concentration of the hydroxyl and the halogenoalkane. And the NH profile diagram is just one stage, okay? And the intermediate is short-lived. It doesn't exist for a long time in the solution. And then we have our intermediate right up there, okay? And then also, students, you must be in a position to remember the fact that once you have your halogenoalkane, okay, where the halogen atom is connected to a carbon with two hydrogens like this, we call it a primary, okay? We call it a primary halogenoalkane. If you have the halogen connected to carbon with only one hydrogen, it becomes secondary, okay? But if there's no hydrogen at all, it becomes tertiary, okay? Which is what we are going to look at. So this is the nucleophilic substitution for a primary halogenoalkane. I've shown the mechanism here. My arrows are so clear. And then we have our product there, which is ethanol, okay? Right, let's move to our tertiary halogenoalkane, and let's see whether the story is going to be the same or it's going to be different. I've done the primary, okay, and we're now going to look at the tertiary, okay? Now, if you're going to come up with a tertiary halogenoalkane, you can come up with something like this, okay? CH3, a methyl group here, and your halogen, okay? Right, so just a quick exercise. What is the name of this halogenoalkane, okay? Right, we can number our longest carbon chain, okay? Our longest carbon chain is 1, 2, 3, okay? And then you have chlorine sitting on carbon number 2 and methyl sitting on carbon number 2, okay? So we would call this one 2-chloro, 2-methyl, okay? Chloro, C comes before M in the alphabet. So the name of this halogenoalkane is actually 2-chloro, okay, 2-chloro, 2-methyl, 2-chloro, 2-methyl propane. So 2-chloro, 2-methyl propane is a tertiary halogenoalkane because the chlorine is connected to a carbon which does not have any hydrogen at all. Chlorine connected to carbon with 2 hydrogens, primary. Chlorine connected to a carbon with 1 hydrogen, secondary. Chlorine connected to carbon with no hydrogen at all, it becomes a tertiary. Okay, so this one is actually a tertiary. Okay, it's actually a tertiary halogenoalkane. That's how we classify it. It's a tertiary halogenoalkane. Okay, so I'll remove the name and then we want to follow what will be happening here. Okay, now our hydroxyl cannot attack the carbon center here. All right, please remember this bond is polar. All right, so again, I'm going to put an arrow here, small positive negative charge, small positive charge there. Okay, because of the movement of electrons in that bond, this is negative, that's positive. Okay, so our hydroxyl, okay, it wants to access that carbon center. Right? It cannot come from here because it will experience repulsion. The only option it could have is to attack from there. But there's a problem. We have bulky groups. Okay? These groups are too large. Okay? They are too large. So if the hydroxy tries to attack from there, it will be prevented from reaching the carbon center because of the bulkiness of the methyl group. In chemistry, we call that steric hindrance. Okay? So from this side, not possible because this one is negatively charged, that is negatively charged. There's bound to be repulsion. From that side, not possible because of steric hindrance. CH3 are bulky groups. So the OH is not going to be able to approach, it's not going to be able to access our carbon center. So we have to suggest another route which we are going to take here. First of all, we're going to have a slow process happening. Okay, we're going to have a slow stage happening here. And this slow stage, okay, will simply be the chlorine moving away. Okay, so the chlorine will move away. Let me just use this red one. The chlorine will move away. Okay, and then we are going to have an intermediate carbocation produced here. Okay, so it will be having this, and then the chlorine moves away. That one is a slow stage. Okay, let me just rub here so that you can see what is happening. Okay, this one is actually a slow stage. Okay, now the chlorine has gone away. Now you can see the carbocation is accessible. And also, what you should remember is this carbon is positively charged. And you know, in organic chemistry, the methyl groups have a tendency of pushing electrons towards, they've an electron donating effect. So it tends to stabilize the intermediate carbocation so that it remains in solution for some time. So that stability of the intermediate carbocation will actually encourage the hydroxyl to attack the intermediate carbocation. So our hydroxyl can now move on. Okay, this is our hydroxyl with its lone pairs. Take note, curly arrow. Okay, so this one is negative, that one is positive. So this stage is fast. That was slow, this now stage is fast. So we have a two-stage process happening here with a slow stage and we have a fast stage. Now in reaction kinetics, when you're dealing with reaction kinetics, if a process has more than one stage and one of them is slow, we consider the one which is slow. The slow stage will affect the whole process. I think even in athletics, when you have a relay team, okay, the success of that team is going to be dependent on the slowest runner. Okay, so they need to be strategic, whether to place the slow runner in the stretch or around the bend. Okay, because the clever coach will know that the success of that team is not affected by the fastest runner, it's affected by the slowest runner. So also in organic chemistry, if you have two stages, okay, stage 1 and you have stage number 2, okay, the speed of this chemical reaction is only going to be affected by the slow stage. So if we are to think reaction kinetic wise, the rate of this reaction is only affected by the concentration of our tertiary halogenoalkane, not on the chlorine, okay? Because the halogenoalkane takes its time for this bond cleavage to occur, all right? So previously we saw our rate expression having two molecules, but this one only has one. The previous one was bimolecular. This one is unimolecular, okay? Because it's unimolecular, we again write it as before, okay? Unimolecular, it's nucleophilic substitution, but only one molecule, so we call this one SN1 mechanism, okay? 2 stages, but we are only concentrating on the slow stage. And if you are to draw the NH profile diagram for this one, you are going to see that it will be 2 stages, okay? Right, so we have a slow stage with a high activation energy, and then we have another reaction which is fast. So we are going to have, okay, EA1. I'll call this one EA1, the first activation energy. And then we have this one, which is EA2, okay? And if you look, EA1, okay, EA1 is greater than EA2, because EA1 takes much longer to occur. So we're going to have our reactors here and our products down there. But the difference now is we have a 2-stage reaction, okay? Simply because, first of all, the chlorine must move away, okay? So I know it can confuse students, okay? Students have a tendency of thinking that it's 2-stage, so it's SN2. It's opposite. 2-stage, SN1. 1-stage, SN2, okay? As long as you remember that, you will not be lost, okay? So we need to remember all these facts. So I'm gonna remove the graph so that I can show you the products that we are going to produce here. Okay, we have done our nucleophilic substitution. So when that has happened, we are going to have a compound of this nature: CH3, OH. Okay, and then we have obviously our sodium chloride in solution, because the OH will be having sodium chloride. Okay, right. Another fast exercise. How do we name this one? We have OH and we have CH3. Okay, again we have carbon 1, 2, 3. Okay, this is an alcohol. Okay, it's actually a tertiary alcohol. Okay, the way we classify alcohols is similar to the way we classify our halogenoalkane. So we have methyl group on carbon number 2 and OH group on carbon number 2 as well. Okay, so this one is propan-2-ol. Okay, propan-2-ol, but it's not complete because our propan-2-ol is a group, a side group. So the complete name will be 2-methyl propan-2-ol. Okay, right. So from 2-chloro, 2-methyl propane, we've produced 2-methyl propan-2-ol, which is also a tertiary alcohol. Okay, in another session, I'll touch on types of alcohols and the reactions that they undergo. Okay, right. So remember, okay, this one is SN1. When we are talking of tertiary halogenoalkanes, there is a 2-stage, and the 2-stage will be represented by SN1. The other one, okay, only 1 stage but bimolecular. I hope you have managed to learn something from the reaction mechanisms and also from the nucleophilic substitution for halogenoalkanes. As I always say, when you've enjoyed this video, don't enjoy it by yourself. Remember to just click this subscribe button and also share. Discuss this video with your friends. I'll be very happy to read your comments in the comment section on how I can improve these videos, how can I do it better so that you students will be in a position to benefit. What is important is at the end of the day, you should be in a position to use these videos. When you don't feel like reading, you just put on your headphone and you listen to the lectures that I am putting in my YouTube channel. Thank you so much. I'll see you in my next video. Thank you so much.